in this computer. All right. So coming back, heat and work, we're going to be taking notes on those. I should have stopped share screen, whiteboard. And then I'm going to pull up the chat here. Thank you. All right. So energy, we're looking at chapter 2 continued. We're looking at chapter 2, part 2, and this is week 3 of class. It's on January 25th. Energy can cross, I'm writing a note here that energy can cross a boundary of a closed system in 2 forms. Heat, which we represent by the letter Q, and work, which we represent by the letter W. As a reminder, because this becomes really important for problems in the next few chapters, including this one, if we have a closed system, it's not open to the air, it's closed, we say this system is a closed system. If we have heat coming out, so this is heat coming out, we are losing heat from the system, this is negative. If we are putting heat into the system, this is positive. If we are putting work, if we are, so now looking at work, if we are generating work by the system, then this is negative. If we are putting work into the system, this is positive. Sorry, that arrow got a little wonky. So I know I went over this in earlier classes, but I think it's important to go over again and then looking at problems because it gets confusing pretty quickly. As a reminder, we can have specific heat, which is our total heat over our unit mass. This is specific heat. What units will specific heat have? Yeah, Justin. So it'll have something like a joule per kilogram as its units. Oh, wait. Yeah, joule per kilogram. Yeah. Kilojoule per kilogram, joule per kilogram, joule per gram, some sort of energy term divided by a mass term. We can also have specific work, which is a lowercase w. It's equal to total work over mass. Specific work. And this will still have units of kilojoules per kilogram, unless there's some sort of time component. If we're looking at energy per time, then it would be in kilowatts. But if we're just looking at basic work, it would be kilojoules per kilogram. When you add time, kilojoules per second, that's where you get to watts. All right, so heat transfer is based on temperature difference. Work is based on force over area, force over distance. So this is based on some sort of force acting on the system. This is based on a temperature difference. Are there any questions about that? Does anyone need more time writing? All right. So coming back to the lecture materials, temperature is a driving force of heat transfer. If you have an ice cold beverage and you leave it on your counter, it will eventually become the same temperature as the room based on heat transfer. There's a temperature differential between my iced tea and the air of the room. So the air is going to be transferring energy into my cold drink to warm it up to the same temperature. Similarly, if this were hot tea, I would be losing heat to the surrounding air, and the air would get a little bit warmer and my tea would get a little bit cooler, and they would meet in the middle. So if you are gaining energy from heat transfer or losing energy from heat transfer, that determines if you're positive or negative. And heat transfer is entirely based on temperature difference. Heat, similar to work, exists at the boundary of a system. So there's not heat transfer occurring through the whole system, it's occurring at the boundary. So heat is leaving the boundary of a closed system at the edge. So we have the 2 kilograms of heat that's moving throughout the system, crossing the boundary from the system to the surrounding. So they exist at the boundary. It's not a super important thing to know, but just in order for you to visualize it and understand fully what's going on, heat and work are existing at the boundary. All right. When we're looking at energy transferred based on heat, and we can look at specific energy, this is related to, here again. This is related to the rate of heat transfer, which is going to be Q with the dot over the top. So heat transfer over time. This is going to be equal to our heat transfer is going to be equal to our integration from time 1 to time 2 of our heat transfer rate times our change in time. So a basic integral of our heat transfer rate over time, so we can figure out how to use it in a basic equation for heat transfer. And here, if our heat transfer rate is constant, if our heat is transferring at the same constant rate over time, it's not a dynamic transfer, it's not a little bit of transferring and then less. If it's at a constant rate, if our heat transfer rate is constant, then this integral becomes Q equals Q rate transfer. Our heat is equal to our rate of heat transfer times our change in time. So this should make sense, right? If we have a certain amount of heat transfer occurring over a certain amount of time, if we multiply that by time, then we get the overall heat transfer rate. So while our heat transfer Q has units of kilojoule, our heat transfer rate is going to have units of kilojoules per second or kilowatts. And then time typically in seconds. Any questions? All right. So I'm going to go ahead and clear this unless anybody needs more time. I also try to save them and upload them just in case you're a little behind. All right. If we're looking at energy equations, this chapter is saying that energy can be transferred across a closed boundary in the form of heat and work. So if we look at the change in energy of a system, the change in energy of some system, which is what we're always looking for, which is why I typically don't write system, because we're looking at a system all the time. We can have work cross the boundary and we can have heat cross the boundary. So we can have a change in heat and a change in work. And that's how, those are the two forms that energy can cross a closed boundary system. We also know that we can have an energy change of a system, of a closed system, where we have our change in kinetic energy plus our change in potential energy plus our change in internal energy, Ke, Pe, and U. These are all uppercase. So in some situations, we can set these equations equal to one another and use it to solve for unknown variables. So one example of that is, this problem takes a lot of work, so I'm going to actually delete this unless anybody needs more time. Right. So an example of this is example 2-10 on page 74 of the 9th edition. It might be on a similar page in the earlier editions. But when you see the description, you'll know the problem. Okay, so I'm going to write the problem statement. It's a little bit long. I'm going to read it as we go. Yes, that was uppercase. Those are all uppercase because those were total energy and total work. But you could write them all lowercase as well if you're including that they're on a per mass basis. So for this example problem, we have a, I'm going to actually pull it up here if I can first so you can see it, and then we'll write it out. So a tank, a rigid tank contains a hot fluid that is being cooled while being stirred by a paddle wheel, this paddle wheel. Initially, the internal energy of the fluid is 800 kilojoules. During cooling, fluid loss, the fluid loses 500 kilojoules of heat, and the paddle wheel does 100 kilojoules of work on the fluid. Determine the final energy of the fluid. Determine the final internal energy of the fluid. So we're trying to solve this problem here. It's example 2-10 in your textbook. I'm gonna work it out here and rewrite part of it. So for this one, we have a rigid tank. So a tank that is not changing shape. A rigid tank contains fluid being cooled. So it's going from a higher temperature to a lower temperature, being cooled and stirred by a paddle wheel. And then initial internal energy is 800 kilojoules. During cooling, the fluid loses 500 kilojoules of heat. The paddle does 100 kilojoules of work. Determine the final internal energy. Determine the final internal energy. So I already showed you the schematic of the picture, but whenever I work problems, I just said this in Fundies for whoever had me for that about 30 minutes ago, I always draw a schematic first and I include what we know and what we don't know. So we have some sort of tank that is being filled with a hot fluid, and it is being stirred by some sort of paddle wheel system. So some sort of, stirring device in this hot tank. The fluid inside has a starting internal energy of 800 kilojoules. And we're looking for the final internal energy. So you can either write U sub I and U sub F, or U sub 1 and U sub 2, whichever nomenclature you prefer. This is a J. Sorry, that's kind of wonky. The system is losing heat of 500 kilojoules. Should this be positive or negative?
Negative.
Yes. Yeah. Negative. Right? Based on the initial drawing, if you're losing heat, it's negative. And then we have our shaft work being done by this paddle. We call this work sub shaft. This is based on the type of work that's being done. It's a shaft type system. So it's based on the torque of the wheel. So the work being done by the shaft is 100 kilojoules, 100 kilojoules. Is this positive or negative? Somebody other than Noah. You're right, Noah. I just want other people to answer too. Thanks, Kaya. Yeah, it's positive. So go back to that little chart that we draw. Yeah, thanks, Jordan. That shows at the beginning of class, and also, just make sure you memorize it. So work is being done on the system, and so it's positive. All right. So we have, I think we have everything we know about this system. Is there anything that maybe I forgot to include? All right, based on logic, do you think the final internal energy will be higher or lower than the starting internal energy? Lower. Yeah, Kaya. Anybody else agree? Layla? Okay. Right, Jordan. Yeah, so it should be lower, right? The system is cooling off. It's losing heat. It's getting cooler. The molecule should be less excited. There should be less internal energy. So it should be lower. That's one thing to check our value. And another thing, why did I just write Q and not Q the rate of heat transfer?
Because there's no time.
There's no time component. We don't have any time component included in this question. If there was a time component, like if we were looking at the system over the course of an hour, then we would be using, the rate of heat transfer, this Q dot here. Great. All right, so moving right along. For this system, we know that our change in internal energy for a closed system, like a closed rigid tank, can be equal to our change in heat plus our change in work. But it can also be equal to, let me collapse this a little bit. It can also be equal to our change in kinetic energy plus our change in potential energy plus our change in internal energy. These are just our basic energy equations that we've been working with. There's no time component here. There's no hat because we don't have a time component included. It is a rigid tank that is sitting still in one position. There's no movement of fluid into and out of the tank. There's no movement of the tank itself. There's no velocity term in this whole question. So there's no kinetic energy that's being included. And I know that this seems to be the hardest part for some people, so I'm going to start writing little notes about it. So this is a rigid tank. Rigid tank. Not moving. No velocity. So especially for change in kinetic energy, you need a change in velocity. If you remember on Friday, we were at a constant velocity. There's no change in velocity, so there's still no kinetic energy included. For a change in potential energy, we need some sort of height change or some sort of influence by gravity by changing height. So we also don't have any potential energy included here. There's no delta H. There's no influence of us changing height. The tank isn't huge. The tank's not on top of a cliff and gonna fall. There's no change in height that's going to happen. So the only thing that we're concerned about is this internal energy term and heat and work. So our equation then becomes our change in heat plus our change in work is going to be equal to our change in internal energy. And this is going to be pretty much the same for all of these rigid tank questions. You're not going to have kinetic or potential energy. These are for moving cars and roller coasters and turbines, not for rigid tanks that are sitting still. So we have our basic equation here. We know that our change in internal energy is going to be equal to our change in heat plus our change in work. We're given a value for heat and we're given a value for work. And we know that our heat is negative 500 kilojoules based on what we wrote here on the diagram. So the heat change throughout our system, the heat is losing 500 kilojoules. Our work being done is 100 kilojoules over in the system. The work that's being done on the system is 100 kilojoules, right? Positive. And this is going to be equal to our change in internal energy. So we have negative 400 kilojoules is equal to our change in internal energy, which is also U2 minus U1. And we know that U1 is 800 kilojoules. So now we have negative 400 kilojoules is equal to U2 minus 800 kilojoules. Solving for U2, we get positive 400 kilojoules. Is this smaller than our starting internal energy? Yes, it is. Does that make sense? Is that what we were expecting? Yes, it does. So we have a lower internal energy for a more cooled system, and it required 100 kilojoules of work to be added to the system, but we also generated some heat. Are there any questions about this? All right, I want you to try it yourself. You try. And this is going to be the same situation, except your final internal energy, we know it to be 1600 kilojoules. Your heat loss, or okay, so your work being done by your paddle, so your shaft work coming in is going to be equal to this time 200 kilojoules. So you have more work being done. And this time we're going to be heating up the water instead of cooling it down. So we're going to have heat coming in, and this is going to be equal to positive 400 kilojoules. We're heating up the system. And I want you to find your starting internal energy. So do the same problem again, but use the new values. Is that clear to everybody? You're heating up a fluid. It's gaining 400 kilojoules of heat. There's a shaft that's doing 200 kilojoules of work to continuously stir the system. And your final internal energy is 1600 kilojoules. What is your starting internal energy? Once you have an answer, please type it in the chat so I can see how many people are done.
What is the last one that you changed? I can't really see it on the whiteboard. underneath the shed.
Can you see it now?
No.
Okay. Let me see.
I can see it now. Sorry, I just had to change my screen a little.
Oh yeah, if you make your screen all the way full size, a lot of times it helps to see stuff, but I'm trying not to write all the way down to the bottom.
Okay.
So Levi, yes, for this chapter, I would always start with a delta energy equation, making sure to include time or any other things that might be given in the equation, and then starting with your change in energy equation and canceling things out. That's where I would start. Seems like about 10 people have an answer, so I'm going to give a few more minutes. Make sure to type it in the chat once you have an answer so I can kind of gauge how done everybody is. All right, seems like most people are done. Most people got 1,000 kilojoules, which could also be what 1 megajoule, but 1,000 kilojoules is right too. So that's great. Are there anybody who didn't get that answer? Anybody that's still kind of confused, wants some clarification, wants to ask a question? All right, awesome. Good job. All right, I'm gonna move on to a slightly different topic, but it's related. We are going to be looking at efficiency, which starts on page 79 in your book. Efficiency we represent by, I don't know what Greek letter this is. Eta, maybe? I'm not sure. It's like that N with the loopy tail. Does anyone know what Greek letter that is? I think it might be Eta.
Efficiency. Yeah.
Yes, this is efficiency. But do you know what Greek letter this is? Let's see, Greek letters. It's not that big of a deal.
It is Ada.
It is Eta. Okay, yeah, it's Eta. Great, there you go. So thanks, Justin. Eta is what we represent efficiency, and it's equal to desired output over required input. Required input. Desired output over required input. So for instance, if you are, I'm trying to think, if you want to get a, I guess the best example of this is for combustion. So if we look at combustion, the energy density of the fuel that you're burning is your required input, and then the amount of heat that you're getting is your desired output. I'm trying to think if there's any other examples in the book, but yeah, that's a good one. So what you're required to put in order for you to get a certain output. And this is rarely 100% because of what law? It's not the first law. The first law is energy conservation. It's the second, Noah. So what's the second law of thermodynamics?
Energy flows from higher quality to lower quality.
Right. So we're always integrate P is always increasing. Available work is always decreasing. We're always losing some energy to heat. So no matter how much coal you burn to power your train, you're going to have to burn more than its potential fuel value to get your desired output, because you're going to lose some towards decreased quality of energy. That's the second law. So here's our efficiency equation. The book goes a lot more through efficiency. I don't think you need to know all the different types of efficiency, but I think you should be familiar with efficiency in general. And please read through the section, because it talks about efficiencies in motors, in generators, in pumps, in turbines, and how they are slightly different and how the equations are different. A lot of that is on page 83 of the 9th chapter of the 9th edition of the textbook. All right, so if we look at example problem, there's an example problem on page 82. It's in the upper corner. It's not labeled with a number, but this example problem is looking at a fan moving through, or air moving through a fan. So it's this question right here. Here's the little schematic. So we have air moving through a fan. For this question, air moves through a fan with a mass transfer rate, M with the hat, mass transfer rate of 0.506 kilograms per second. Is that a mass transfer unit? Yes, it is. It's a mass per time. So mass mass rate of mass transfer. The fan does 50 watts of work. The fan does 50 watts of work. Is this an energy unit or a power unit? Is this an energy unit or a power unit? 50 watts.
Power.
Power, right. So it's joules per second. It's 50 joules per second of power. Yeah. The velocity leaving the fan, the velocity of the air leaving the fan, the velocity leaving the fan is steady at 12.1 meters per second. The fan is at 1 atm, so it's just at basic atmospheric pressure. And any pressure change in the system is negligible, any pressure change throughout the fan. What is the efficiency? What is the efficiency of the fan? Okay, so I always like to draw a diagram. We have some sort of fan, right? Here's a fan blade. We have air that's moving out of the fan. So I'm going to label this side of the fan as 0.1 and this side of the fan is 0.2. I'll draw my fan in a circle and maybe like try to make it look a little more like a fan. That's not super helpful, but this is a fan. All right, so I know the mass flow rate of the air coming out of this fan is 0.506 kilograms per second. I know that my pressure at 0.1 is going to be equal to my pressure at 0.2, which is going to be equal to 1 atm. But also this means that the change in pressure is equal to 0. I know that my height at 0.1, which is, you can do Z or H, is equal to my height at 0.2. The book uses Z, that's why I'm writing Z. And so my change in height is equal to 0. I can't really scroll down. This whiteboard is not good, but if you do this little expand thing here, it might help you. Can you see better now? Okay, I'll try not to write any lower than that. This is a Z. I know that my velocity at 0.2 is equal to 12.1 meters per second. But what is my velocity of air at 0.1 on the other side of the fan? Or what can I approximate it to be? Yeah, Elizabeth and Connor, yeah, we can approximate this to be 0. This air before it's coming out of the fan is going to be not really moving around at all, assuming that you're inside or in a place that the air is not really moving. So we can approximate this to be 0 meters per second. Even if it's moving a little bit, it's moving so much slower than 12.1 meters per second that we can just approximate it to be 0. Yeah. All right. Anything else that we know that I haven't maybe included in the diagram? Work. Oh yeah, you're right. So the work being done by the fan, we can include maybe like a work pointy thing here. So the work being done by the fan is 50 watts. Anything else I'm missing? Is this positive or negative? Positive. Anybody else agree? Layla, it's positive. Anybody think it's negative? Okay, yeah, it's positive because there's work being done by the system, or by the surroundings to the system. Right? There's work coming in. It's not generating work that's going out. All right. So we're asked to find the efficiency, which we know this efficiency is going to be mechanical efficiency, and it's going to be mechanical efficiency of a fan, or something similar to like a shaft type system, right? Like the torque of the arm is moving the fan. So this is still going to be our basic equation of output over input. Oh. And here we're going to have for our input, what is our input going to be? Justin says work. Anybody think it's something else? Christian agrees. Yeah, it is going to be work, right? So the input here is going to be our work. And what's going to be our output?
Kinetic energy.
Say that again.
Be the kinetic energy produced.
It is going to be kinetic energy produced. Yeah, but taking a step back, we can even just put that it's going to be our energy, but I'm going to say it's our change in energy over time of our mechanical system, because that's how it's written in the book. So our energy changing over time of our mechanical system, because we do have some time components for this problem per second. All right. If we look at our energy equation, our change in energy per time is also our change in I'm sorry, hold on, don't write that yet. I wrote my delta too early. Our change in energy over time is also equal to our mass flow rate times our change in specific energy, right? This is an equation that we've worked on before, where our change in energy, our total change in energy over time is going to be equal to our mass flow rate times our change in specific energy. This is still going to be divided by work. And our specific energy equation is going to be our change in specific kinetic energy plus our change in specific potential energy plus our change in specific potential energy, kinetic, potential, and internal specific energies. We're changing them over time over our work. So for this problem, what can we cancel? Kinetic, potential, or internal energy? Yeah, Noah's right. We can cancel potential energy because we have no height change. There's no change in height. No delta Z. No change in height. There's no gravity component. There's no height component. There's no change in height. Can we cancel anything else? Yeah, Elizabeth. So we can cancel internal energy. There's probably a little bit of internal energy changing when we're, speeding up and putting it through the fan, maybe cooling it off a little bit. but the change overall here is going to be negligible. We're going to ignore any internal energy change. So we're going to say change is very small, about 0. We're not really heating up a closed tank. We're not really looking at our fluid flow of our system because our pressure is equal to 0. There's no pressure drop. We're not pressurizing the system. There's no real internal energy indicators that are occurring here. So then our equation, as I think Justin or somebody first suggested, really just becomes this kinetic energy term. And our kinetic energy term is going to be our change in velocity times 1/2. And we already know our change in velocity because it's 0 to 12.1. We know our mass transfer, our mass flow rate because we're given that value, and we know value for work. So is there anything missing from the equation, or can we plug in chug? So there's nothing missing, right? We know mass transfer rate, we know kinetic energy equation because we know change in velocity, and we were given work in our problem statement. So now we can just say our mass transfer rate times our change in kinetic energy, specific kinetic energy, this is a lowercase k, over our work done by a shaft put in. And I'm going to denote this as a hat because our work is given to us in kilowatts, which means it's joules per time. So it's actually power. And so this equation becomes our mass transfer rate, and then 1/2 velocity at 0.2 squared minus velocity at 0.1 squared, which is just our change in velocity equation, over our work done by our shaft put in, which is just denoting that it's going to be positive. We know our mass flow rate is 0.506 kilograms per second. 1/2, I'm going to run out of room. Velocity at 0.1 is 0, so we're only looking at our velocity at 0.2, which is 12.1 meters per second squared. And our shaft work here is 50 watts. What are units of watts in terms of kilograms and seconds?
Isn't it like kilogram meter squared per second? Second cubed?
Yep, second cubed, right? So here we have kilogram, meters squared, second squared, so second cubed. So our top value gives us kilograms meter squared per second cubed, and our bottom value gives us watts. Do those cancel? Yeah, so that cancels, right? So our value, when you plug these into your calculator, you get 0.741 kilograms meters squared per second cubed over watts. This is a watt. You need to memorize that if you haven't already. So thank you for whoever answered. I can't really see like names very quickly, but thank you. So a watt over a watt cancels, and our efficiency just becomes a unitless value, which is correct. We can also look at it as a percentage, so 74%. But here's our efficiency for this fan. Of our mechanical fan. Are there any questions about efficiency?
So is there like since it's unitless or whatever, basically does that mean that if like the closer the number that you get for efficiency, the closer it is to 1, well, it can never be 100, right? So it's always going to be like more efficient if it's closer to 1.
Right. So sometimes we can say assume 100% efficiency. We did that in fundies this morning. You'll probably do it in fundies again. And that means that you're going to assume your efficiency is 1, but your value should always be between 0 and 1. So it's always going to be some decimal value, and it's never going to be above 1. It's probably not going to be 1 unless you're making some assumptions. And efficiency is unitless. So your unit should always cancel. It should be unitless. And you can also represent it as a percentage. So 0.74 would be 74%.
Okay, thank you.
On page 82 and 83 in your textbook, it goes over efficiencies for different pumps, turbines, how you can manipulate the equation of output over input for different situations. Please read those on your own. I don't feel like we have time in class to really go over them individually. And you don't really have to memorize them or know them that well if you understand what is your input and what is your output for all of these systems. All right. Any other questions? Does anyone need time writing? Okay, I'm going to go over one more example problem and then we're done for the day. So this example is on page, it starts on page 83. I'm only doing the second part of the example, but this is example 2-15. One thing that helps me if you're struggling is I go through these example problems and I write them myself. Throughout the chapter, I write them myself in my notes. And then I'll go back through and maybe change a couple of numbers and try to work it again and see if I can do it without like using the book or my notes. So that might help you as well, just as a suggestion. All right, so for this question, we're looking at a hydraulic turbine, which is similar to the one that we looked at an example problem on Friday. We have it like operating, we have a lake up here and a lake down here, and we have a turbine with the water, just gravity flowing through the system. And we know for this turbine, a turbine is found to have the, let me move the chat. The turbine is found to have the rate at which mechanical energy of water is supplied to be, so a turbine is found to have the rate at which mechanical energy is supplied to be, sorry if that English is weird. I'm trying to rework the problem a little bit. It's found to be 1,031 kilowatts. If the mechanical power, if the mechanical power output, if the mechanical power output of the turbine is 800 kilowatts, and the electrical power generation is 750 kilowatts, and the electrical power generation is 750 kilowatts. Determine the turbine efficiency, and the combined turbine generator generator efficiency. So we're asked to find two efficiencies of this system that has a turbine and a generator. The turbine water is flowing down from the lake at the top of the reservoir down to the bottom reservoir. It's flowing through this turbine, and the turbine is spinning a shaft to generate energy through the generator. So we know that the total energy change of the system is 1,031 kilowatts. We know that the power output of the turbine is 800 kilowatts, and we know the electrical power generation of this generator is 750 kilowatts. So we want to determine the efficiency of this turbine and of this turbine generator combo. All right, so for the efficiency of the turbine, we're going to be doing our output over input. And in the reverse from the last example problem, with a turbine, we're actually trying to generate power. We're trying to create power, transfer power from the system to the surroundings. So for this one, our output is actually going to be our work done over time. That's electrical. Or I'm sorry, our work done over time. For this one, it's shaft because it's just the turbine. So the turbine has that, power that's happening over our moment arm that's applying some torque and turning that generator. So there's some sort of shaft work that's being done, and it's going out, right? It's negative. We're producing work that's going out. But for efficiency, we don't really care that much about positive and negative. We just know that that work is coming out of our system to the surroundings. And our input for the turbine is going to be our energy over time of the fluid flowing through the system, through the turbine. So our mechanical energy over time of that fluid. So our output this time is work, and our input is energy of the water flowing. And we know from Friday's problem that this equation is the potential energy of the system, but we don't need to work it out because we were already supplied with the value. So now we know that the work being done by the shaft is given to us by the turbine to be 800 kilowatts. And the total energy of the system over time, so kilojoules per second over time, is 1,031 kilowatts, which gives 0.776, or about 77.6% efficient for the turbine. Sorry, that's a percentage sign. So when you're trying to figure out output and input, think about your system. What's coming out, what's coming in, what's the point of your thermodynamic system? What's the fan or the turbine accomplishing? And that's how you're going to determine your input and output. When we're looking at the efficiency in part 2, and this would be for the turbine generator combo, I'm just going to write turbine gen. Once again, we're going to look at output over input. And I want you to try to write the next steps. I'll give you a couple of minutes and then we'll go over it. So try to determine what the efficiency of the combined turbine and generator are. And type it in the chat box once you have an answer. No, it's not 93%. Yes, Connor, it's 72.7, yeah. So everybody else's, you get your answer, type it in the chat box, please. Great. Yeah, it seems like we've kind of reached a critical mass. So yeah, that's great. So for here, our output of the system is still going to be our shaft work that's done by the turbine generator. So this is technically negative, but it doesn't really matter for efficiency. And then we're going to have that same energy over time component for our mechanical system. And we are going to be plugging in the same value for our energy that's being supplied total. But here we're told that the power generation, the overall electrical power generation is only 750 kilowatts. 750 kilowatts, which gives us 0.727 or 72.7%. So in this system, we have some sort of reservoir one up here. It's flowing down through a turbine system here to reservoir two. This turbine is using shaft work to power a generator that's making electricity. So this is a generator, this is a turbine. Turbine. The water that's flowing through here, this is mostly based on this height change here, and the overall energy that is being supplied by the fluid movement is going to be 1,031 kilowatts. But then the power that's actually being produced by the turbine is only reduced down to 800 kilowatts. And then the power that the turbine is able to give to the generator to produce power, electrical power, is only 750 kilowatts. So as we're moving from this fluid and the potential energy this fluid has, while we can generate up to 1,031 kilowatts, when we actually try to produce power, we lose some valuable energy and we end up only being able to produce 750 kilowatts of usable power. Then that power is going to go to your home. You're going to plug it into your washing machine and you're going to lose even more energy over time. So that energy is just cascading down from useful systems into less and less available energy and power. That's the second law. Okay. So that example problem was on page 83 and 84 of the 9th edition. I think it's the same for the 8th edition and similar for the earlier editions. Those are all the example problems I have for today. So you have homework 2 that is due on Friday. I will post this recording along with the notes from this recording under the module for this week. There is also the PowerPoints that I kind of was jumping through between. Yes, Layla, you can start on the second half of the homework. There are still 2 questions related to heat transfer that I'm going to go over on Wednesday. But if you read the special topics in the book, you can do those questions on your own. It's just applying the heat transfer equations. And there is, oh yeah, so the PowerPoints are on Canvas, the PDF PowerPoints, but remember you can skip over the sections that are including electrical work. I decided to skip it for this year. So are there any questions? There's no questions from anyone? All right. Well, then I hope you have a good rest of your Monday. Get started on the homework and you can finish it on Wednesday and have a good day.
Have a good day.